Systems, this is Nav.
Go ahead, Nav.
Yeah, we see the expected sharp shift upward and the Doppler residuals indicating the main engine has started.
Copy that. That's good news. We're still awaiting confirmation of that in the tone. All stations on Juno Accord. This time we see the tone for minimum burn timer. Almost there. All stations on Juno Accord. We have the tone for burn cutoff on Delta B. Grazie mum, Juno. Welcome to Jupiter.
Burn time was 21:02 seconds, only differing 1 second off of the pre-burn predictions.
What a feeling. A mission of this complexity to accomplish tonight is just truly amazing. And it really highlights the partnership and the teamwork between NASA and our contractors and our partners to be able to achieve this amazing, amazing mission.
So tonight, through tones, Juno sang to us, and it was a song of perfection.
The team, the amount of time and effort everyone put into this, and the risks that were overcome, it's amazing. I mean, the more you know about the mission, you know just how tricky this was, and to have it be flawless, I mean, I really can't put it into words.
And you see a handful of people up here, but what we represent is a team of almost 900 people that built and launched Juno, and roughly 300 people that operated it and got us all the way through into Jupiter orbit tonight.
Putting an orbiter around Jupiter is, that's the reason we all go into this profession, is it's science fiction and yet it's fact.
You get a really great dedicated team of a lot of people working really hard for a really long time. You can do some amazing things.
NASA did it again. We're in orbit. We conquered Jupiter.
Good evening. Jupiter is now on display in the southeastern sky during the early hours. It is the brightest object in the night sky and presently lies just below the main body of Leo, the celestial lion, so the planet cannot be mistaken. Here are some recent images of Jupiter. The first is from my friend Trevor Barry of Broken Hill, Australia. And as you can see, there is a lot of detail on show at the moment. Jupiter is the fifth planet in order of distance from the Sun and the giant gaseous member of our solar system. Even a small telescope is enough to show some of the horizontal cloud bands, while binoculars will reveal the planet's star-like moons as they change positions around Jupiter with each passing hour. The planet is at the centre of attention at the moment. While many of you are taking images and observing the cloud features, the NASA spacecraft Juno is closing in on the giant planet and will go into orbit around Jupiter in July. In the coming weeks, you can expect a build-up of spectacular images taken by Juno as the spacecraft closes in on its target. These will be enhanced by your own splendid images and observations of Jupiter as the planet reaches opposition on the 8th of March, when it will be best placed for observations. Juno was launched in August 2011 and is now coming to the end of its 5-year cruise to Jupiter, with its arrival expected on the 4th of July 2016. The spacecraft will have travelled over a distance of 1.7 billion miles.
There are many theories about the origins of Jupiter. here's what we think happened. Nearly 5 billion years ago, a star in our galaxy exploded. The explosion caused a nearby cloud of gas and dust to collapse and flatten into a spinning disk. Most of the gas and dust collected into a hot, dense core that became our sun. The remaining debris formed the planets and other small bodies in our solar system. And the majority of that debris came together to form the giant planet, Jupiter. Of all the 8 planets, we believe Jupiter formed first. Understanding the formation of Jupiter is essential to understanding the origins of our entire solar system, the formation of Earth, and the most basic foundations of life as we know it. Jupiter is 1,300 times the volume of Earth, more than twice the mass of all the other planets combined, the 5th planet from the Sun, and the largest planet in our solar system. Because of its enormous size and powerful gravity, it is believed that Jupiter has influenced the formation and evolution of the other bodies that orbit our Sun. Unlike Earth and the other smaller planets, the composition of Jupiter has remained unchanged since the solar system began. Like a time capsule, Jupiter can help us reconstruct nearly 5 billion years of history. Mission Juno will help prove or disprove theories about the types and amounts of materials that contribute to the composition of Jupiter. By peering beneath its clouds and discovering what Jupiter is truly like, Juno will also test our ideas about the formation of planets, as well as other major secrets of our solar system. Measuring the amount of water in Jupiter will help us understand how and where in our solar system the giant planet formed. Mapping the gravity and magnetic fields of Jupiter teaches us about the planet's hidden interior and whether it has a solid core. In our quest to unlock the history of the planets, Jupiter is the gateway, and Juno holds the key. Hundreds of scientists and engineers in 5 countries have been working for more than 10 years to design and build the Juno spacecraft. This solar-powered probe will travel 400 million miles into space with instruments uniquely built to withstand deadly radiation and the fiercely cold environment of Jupiter. Juno will conduct an unprecedented examination of the atmosphere, the interior, and the vast magnetic field of the giant planet. On August 5, 2011, one of the world's most powerful rockets is set to take off. The Atlas V 551 rocket, weighing 650 tons, launches and reaches a top speed of 4,500 miles per hour. The rocket hurtles through Earth's atmosphere, exhausting its fuel and reaching orbit in just over 10 minutes. The payload fairing falls away, revealing the Juno spacecraft within. Once in its proper orbit, the Centaur booster gives the probe its spin and sets Juno free on its journey to Jupiter. In the shadow of our planet, the spinning Juno spacecraft deploys its 3 massive solar arrays, which will power the mission for the next 6 years. After these arrays lock into place, power from the sun streams into the circuits of Juno for the first time. Escaping the gravitational pull of Earth, Juno is still held to its trajectory by the sun's gravity. The Juno spacecraft is carried 50 million miles into space, as far as the orbit of Mars. A burn from the main engine directs Juno back toward Earth for a final encounter with its home planet. Using Earth's gravity for energy, Juno slingshots into space, increasing its speed and receiving the boost it needs to pull away from the sun and coast all the way to Jupiter. After 5 years of being alone in space, Juno approaches Jupiter and begins reaching a top speed of 160,000 miles per hour, officially becoming the fastest man-made object in history. The main engine ignites to slow down the spacecraft, and Juno is captured by the powerful gravitational pull of Jupiter. Settling into the most challenging orbit ever attempted, Juno will come as close as 3,100 miles to the planet's cloud tops. Juno will continually duck below deadly radiation belts as it studies Jupiter in unprecedented detail for more than a year. Juno will use remote sensing to inspect Jupiter from its innermost core to the outer reaches of the magnetic bubble the giant planet inhabits. Juno will be the first probe to visit the regions above the poles of Jupiter, witnessing energies in the magnetosphere that create its extraordinary ultraviolet auroras. After orbiting Jupiter for over a year, the Juno craft will dive deep into the atmosphere and burn up. But the mission will never truly end. No matter how many answers we find, there will always be more questions. Our search for understanding and meaning continues.
With an equatorial diameter of almost 89,000 miles, Jupiter is the giant planet of our solar system and lies beyond the main asteroid belt 483 million miles out from the Sun. The orbital velocity is less than that of the Earth, so it takes almost 12 years to orbit around the Sun. The surface is dominated by dark belts and bright zones, all of which are variable, although in general their latitudes do not change much. There are also various features, notably the Great Red Spot. Jupiter has 67 moons. The largest of these were discovered by the Italian astronomer Galileo Galilei in 1609: Io, Europa, Ganymede and Callisto. They are also known as the Galilean satellites, and they can be seen in binoculars as they change positions around the planet. Jupiter has the shortest day of all the planets. It is not possible to give an overall value for the rotation period because Jupiter does not spin in the same way a solid body would do. The equatorial zone has a shorter period than the rest of the planet. Conventionally, System 1 refers to the region between the north edge of the south equatorial belt and the south edge of the north equatorial belt. The mean period here is 9 hours and 50 minutes. The most prominent belt is generally the north equatorial, while the south equatorial belt is very variable and may become obscure at times. Outbreaks in the south equatorial belt are the most spectacular phenomenon seen on Jupiter. They involve sudden outbreaks of bright and dark clouds and intense turbulence and many spots moving on rapid currents. The wind speed in the clouds is very intense. In the equatorial region, the wind blows west to east at about 300 feet a second relative to the core, reaching maximum speed about 7 degrees north and south of the equator. In the northern hemisphere, the east wind decreases with increasing latitude until at 18 degrees north, the clouds are moving westward at 75 feet a second. In the southern hemisphere, the conditions are not quite the same, due to the presence of the Great Red Spot. But in both hemispheres, there is an alternating pattern of eastward and westward jet streams, which marks the boundaries of the visible belts. Spots such as the Great Red Spot circulate west or eastward as if rolling between the jet streams. The Great Red Spot is undoubtedly the most famous feature on Jupiter. Together with its characteristic hollow, it has certainly been in existence for nearly 2 centuries and possibly much longer. Here are some images of Jupiter showing the Great Red Spot nicely. It was seen several times during the 19th century, following the first observations of the hollow in 1831 by the German astronomer Samuel Schweppe. At its greatest extent, it is said to measure 24,800 miles in an east-west direction and 8,700 miles north-south, giving it a greater surface area than that of the Earth. The latitude varies little from a value of 22 degrees south, but the spot drifts around in longitude. The Great Red Spot is a phenomenon of the weather in Jupiter's atmosphere. It is a high-level vortex, in other words, a whirlwind, with wind speeds of up to 225 miles per hour. To the south, the spot is bounded by an eastward wind, while to the north it is bounded by a strong westward wind. This means that as the winds are deflected around the spot, they set up anti-clockwise rotation. In the 1960s, the period was 12 days at the outer edge and 9 days inside the red spot. The vortex is a high-pressure area 5 miles above the nearby cloud deck, caused by the upward convection of warmer gases from below. The cause of the red colour is not known. It may be due to the condensation of phosphorus or sulfur compounds at the cloud tops. The ovals in the south temperate zone have proved to be of great importance. Several began to form in 1939 and eventually formed 3 definite features. During the Voyager flybys, they extended about 5,600 miles from east to west and 3,100 miles from north to south, rotating every 5 days. The interior of Jupiter is extremely hot and due to the huge atmospheric pressure is very dense. In 1923 and 1924, a classic series of papers by Sir Harold Jeffreys, who was an English mathematician, proposed a model in which Jupiter would have a rocky core, a mantle composed of solid water ice and carbon dioxide, and a very deep atmosphere. Today, planet scientists believe that Jupiter's core is much more massive than the Earth, where the temperature is of the order of 25,000 degrees centigrade, and the central pressure is up to 100 million Earth atmospheres. The mass of the core has been estimated at 12 to 45 times the Earth's mass. Surrounding the core, there is thought to be a thick layer of hydrogen, which at such pressure will be in a metallic state. At about 29,000 miles from the core, the temperature is about 20,000 degrees centigrade, and there is a transition from liquid metallic hydrogen to liquid molecular hydrogen. In the transition region, the temperature is assumed to be around 11,000 degrees centigrade, with a pressure about 3 million times that of the Earth's at sea level. Above the liquid molecular hydrogen comes the gaseous atmosphere, which is over 620 miles deep. The change in state is gradual. There is no hard, sharp boundary, so that we cannot say where the atmosphere ends and the actual body of Jupiter begins. Pass the light of Jupiter through a glass prism or a diffraction grating, and you get a spectrum. Here is a spectrum of Jupiter taken by my friend Hugh Allen. He has compared the normalized spectrum of Jupiter to that of reflected moonlight, which helps highlight the methane and ammonia absorption bands in the light from Jupiter. Methane is CH4 and ammonia NH3 on the illustration, while hydrogen alpha is centered on the 6562 angstrom units shown along the bottom of the illustration. Jupiter radiates 1.7 times more energy than it would do if it depended only upon radiation it receives from the Sun. Probably this excess heat is nothing more than what remains of the heat generated when Jupiter was formed. It has been suggested that the globe is slowly contracting with the release of energy, but this explanation is not now generally favoured. The Juno space probe will try to solve this mystery. In October 1989, the Galileo spacecraft was launched. It was made up of an orbiter designed to assume a closed path around Jupiter and transmit data, and an entry probe to plunge into the clouds and send back results until being destroyed. On the 7th of December 1995, the entry probe met the Jovian atmosphere at a latitude of 6.5 degrees north and transmitted for an hour before losing contact. By then, it had penetrated to a depth of about 370 miles below the tenuous upper reaches of the planet's atmosphere. The results were in some ways unexpected. Only one distinct cloud layer was found, apparently corresponding to the previously predicted cloud layer of ammonium hydrosulfide. However, one major surprise concerned the winds. It had been suspected that the strong Jovian winds about 240 miles an hour at the entry level, were more or less confined to the upper atmosphere, but Galileo showed that this was not the case. The velocity increased to over 310 miles an hour below the visible level. This seems to indicate that the planet's winds are not produced by solar heating as on Earth, or by the condensation of water vapor. It is now more likely that the cause is heat escaping from the deep interior of Jupiter. The atmosphere was found to be much drier than had been expected. There are large, dark, dry, clear areas known as hotspots near the Jovian equator, and the entry probe plunged into one of these. They are caused by waves of up and down winds. The temperature at their visible depths is only 0 degrees centigrade. Lightning is very intense on Jupiter. Enormous bursts were recorded on the planet's night side by the Galileo orbiter in November 1996, with individual flashes hundreds of miles across. The flashes are of the cloud-to-cloud variety, and no doubt there is thunder as well. Auroras are also intense. They were first detected in 1977 and were recorded by Voyager 1 during its passage across the night side of the planet in March 1979. Radio emissions from Jupiter were discovered in 1955 by Bernard Burke and Kenneth Franklin of the Carnegie Institute. The frequency of the radiation was 22 MHz. Bursts of radiation sometimes made Jupiter the brightest source in the sky at this wavelength, apart from the Sun. The bursts of noise from these distinct areas provided the first evidence for a Jovian magnetic field. On the sunward side of Jupiter, the field tends to be compressed. On the night side, it is stretched out into a magnetotail, which may be up to 400 million miles long, so that at times it may even engulf the ringed planet Saturn. There are zones of intense radiation at least 10,000 times more powerful than the Van Allen zones surrounding the Earth. Pioneer 10, the first space probe to encounter these zones in December 1972, received a total of over 250,000 rads. Sadly, a dose of 500 rads is fatal to us humans, so future space travelers will need to be protected. In 1964, the Australian meteorologist K.E. Bigg realized the orbital position of Io has a marked effect on Jupiter's radiation, and it is now known that the satellite is connected to Jupiter by a very strong flux tube, setting up a potential difference of 400,000 volts. Molecules are ejected off Io's surface by particles in the magnetosphere, producing a torus tilted to Io's orbit by 7 degrees, so that Io passes through it twice for each rotation of Jupiter. There is also a tenuous sodium cloud around Io, which extends all around its orbital path. Jupiter's ring system was discovered in March 1979 by a single image sent back by Voyager 1 as it passed through the equatorial plane of the planet. They have since been detected with the Hubble Space Telescope and studied in detail with the Galileo spacecraft. The rings are very dark and are quite unlike the bright icy rings of Saturn. They are caused by material coming from the small inner satellites. This dark, slightly reddish material is thrown off the surface of the satellites following impact by meteoroids travelling at speeds greatly enhanced by Jupiter's strong gravitational pull. The outer Gossamer ring is actually composed of two faint and more or less uniform rings, one enclosing the other. They extend from the outer boundary of the main ring at 80,000 miles and extend to over 138,000 miles. Although the ring is so fragile, it is difficult to give a precise boundary. Results from the Voyager and Galileo spacecraft show that the rings are much brighter in forward scattered light than in back scattered or reflected light. This indicates that the ring particles are only about 1 to 2 miles across. There have only been 4 NASA missions dedicated to studying the planet Jupiter. Pioneer 10 and 11 in 1972, the Voyager space probes of 1977, and the successful Galileo space probe. NASA's Juno mission is therefore long overdue. Juno will go into orbit around Jupiter on the 4th of July 2016 and will carry out experiments during its 5-year mission.
The Jupiter orbit insertion burn is a mission-critical event. Arrival is timed to provide dual DSN station coverage with the Goldstone and Canberra tracking complexes and to correspond to a minimum in Jupiter's magnetic field, thus reducing the electromagnetic effects of a spinning spacecraft on key engineering subsystems. During the execution of the insertion burn, the flight system turns to a fixed burn direction and increases its spin rate before firing the main engine. The entire orbit insertion critical sequence is performed in view of the Earth. Subcarrier tones from a toroidal antenna provide the flight operations team with necessary engineering information. The insertion burn places Juno into a 78-day capture orbit with apogee at a distance of 145 Jupiter radii. A fourth and final main engine burn is required to reduce to an 11-day orbit period for science operations. The apogee of this orbit is at a distance of approximately 39 Jupiter radii with perigee at a distance of approximately 4,500 kilometers. The first of 2 science orbit types, called an MWR orbit, is exercised on orbits 3 and 5 through 8 and is characterized by a flight system attitude in which the spin plane passes through the center of Jupiter. This attitude allows Juno to observe Jupiter's aurora and atmosphere during the perigee passage. The second science orbit type, called a gravity science orbit, is exercised on orbits 4 and 9 through 32 and is characterized by a flight system attitude in which two-way Doppler X-band and Ka band links are maintained with the DSN tracking station on Earth for the duration of the perigee pass. The Doppler measurements are essential for determining the distribution of Jupiter's mass. Juno's fields and particles instruments participate in both science orbit types, obtaining measurements of Jupiter's magnetic fields, plasma waves, and radio emissions. As Juno travels through the Jupiter system, it becomes an integral part of the resident magnetic environment, enabling it to observe phenomena along field lines that carry extraordinary amounts of energy crashing into Jupiter's polar regions. The orbital trajectory is designed such that during the perigee passage of orbits 3 through 17, a global map is obtained at 24 degrees spacing and longitude. With an 11-day orbit, the Jupiter longitude of each successive perigee is designed to differ from the previous one by 192 degrees. After 15 science orbits, the map is complete at 24 degrees spacing. An offset of 12 degrees in longitude is implemented before starting another 15 orbits, continuing with orbit-to-orbit increments of 192 degrees. With the perigee passages of orbits 18 through 32, the 24-degree spacing is split in half, resulting in a final global map with 12 degrees longitudinal spacing. Orbit 33 provides a perigee pass that is held in reserve. It is designed to replace any longitude that may have been missed due to an anomalous behavior on any single perigee of the previous 30 orbits. A deorbit maneuver is performed near apogee of the 33rd orbit, placing the flight system on a path for impact with Jupiter in compliance with planetary protection requirements.
Looking to the future, there is growing excitement among space scientists who want to explore Europa and Ganymede for signs of life, as there is strong evidence that they have an ocean beneath their surface. When the Italian astronomer Galileo Galilei turned the first telescope towards Jupiter and discovered the planet's 4 large moons, he had no idea that they would turn out to be worlds of such great importance. The 4 main moons of Jupiter, Io, Europa, Ganymede and Callisto, are as different from one another as they can be. They are of fire and ice. Io is volcanically active with sulfur volcanoes. Europa has an icy surface with linear grooves, while both Ganymede and Callisto are both rocky in composition. Io is the innermost of the 4 Galilean moons of Jupiter, and with a diameter of over 2,260 miles, is the 4th largest moon in the solar system. Europa, the second of the 4 Galilean moons, is the second closest to Jupiter and the smallest at about 1,940 miles in diameter, which is slightly smaller than the moon. Ganymede is the largest natural satellite in the solar system at 3,270 miles in diameter, which makes it larger than the planet Mercury, although it only has about half the mass. Callisto is the 4th and last Galilean moon. It is the second largest of the 4, and at just under 3,000 miles in diameter, it is the 3rd largest moon in the solar system. In June 2015, NASA's mission concept to conduct a detailed survey of Europa and investigate its habitability successfully completed its first major review by the Space Agency and is now in the development stage. The spacecraft would orbit around Jupiter every 2 weeks, providing opportunities for close flybys of Europa. The mission plan includes 45 flybys, during which the spacecraft would image the moon's icy surface at high resolution, investigate its composition and the structure of its interior.
NASA announced on Wednesday that its mission to Jupiter's moon Europa is moving to a development phase.
Europa is the most likely place to find life in our solar system today, because we think there's a liquid water ocean beneath its surface.
In the 1990s, NASA's Galileo mission found strong evidence of an ocean underneath Europa's crust.
We might be actually looking at a body that is presently alive, presently active, and presently undergoing its geology. There is too much evidence right now lying around on the surface, the red stuff, that suggests that something's going on there. Is that an environment that is habitable for any sort of life form? By golly, we really have got to go back and figure that out.
According to the mission plan, a spacecraft would orbit Jupiter bi-weekly and collect data during close flybys of Europa.
Previous mission concepts were for a spacecraft that would orbit Europa, but Europa is bathed in radiation from Jupiter. Any mission that goes in the vicinity of Europa is cooked pretty quickly. Instead, we're looking at a mission that will orbit Jupiter, make close flybys of Europa, and then zip out of the high radiation region.
NASA notes that there will be 45 flybys during which the spacecraft would image the moon's icy surface at high resolution and investigate its composition and the structure of its interior and icy shell.
Images from the Hubble Space Telescope tells us that Europa might be erupting plumes of water high into space. If that's true, then we could fly through those plumes with a spacecraft and literally taste it to understand the composition of Europa's interior.
The spacecraft launch is planned in 2020s with arrival in Jupiter's orbit several years later.
Europa is so important because we want to understand, are we alone in the cosmos? If there's life in Europa, it almost certainly was completely independent from the origin of life on Earth. That would mean the origin of life must be pretty easy throughout the galaxy and beyond.
On the 9th of December 2015, the European Space Agency signed a development contract with Airbus defense and design for the JUICE mission. JUICE, Jupiter Icy Moons Explorer, was selected in May 2012 as the first large-class mission within ESA's Cosmic Vision program and is planned to launch in 2022 to arrive at the giant planet in 2030. So that 14 years from now, we will have two magnificent spacecraft in orbit around Jupiter studying the planet's moons in the search for life. The theme for JUICE is the emergence of habitable worlds around gas giants. The mission will perform detailed investigations of Jupiter and its system with particular emphasis on Ganymede as a planetary body and potential habitat. Callisto will be explored as a witness to the bombardment history of the early solar system. On the next clear night, do go outdoors and see Jupiter. Turn your telescope towards the planet and view the horizontal clouds through the eyepiece and watch the Galilean moons as they change positions around the giant planet. Wonder in amazement at what we have learned about Jupiter over the last 400 years, and even now there are more mysteries waiting to be uncovered. And remember too that there could be life beneath the rugged icy surface of Europa. That is all we have time for this month. Please visit our website, Vimeo, where you can watch all of the past shows of astronomy and space. And if you like this program, please share it with your friends and members of your local astronomical society. Until we come back next month, good evening.